Hello, welcome to the first video to accompany the Further Maths Conference Complex Numbers session. In this video, we're going to consider why we want to explore complex numbers at all, and look at some of the simple things we can do with them. Take a look at these equations. Pause the video for a moment while you write down the solutions. OK, look at your solutions. What types of number have you used to solve these equations? You may have said either natural numbers or integers for the first one, then fractions or rational numbers. The third one requires us to venture into irrational numbers, so that now we have the set of real numbers. What about the last one? You may have said that it was impossible, or that you needed imaginary or complex numbers to solve it. Let's take a quick look at how these types of numbers relate to each other. So, first we have the natural numbers, and usually we include 0 in here. That's a subset of the integers, which is a subset of the rational numbers, which is a subset of the real numbers. And once we start including I, the square root of -1, we're expanding further into complex numbers. Textbooks rarely show this, but it's worth sharing with students. Are you comfortable with the positioning of all these numbers? How would you explain to students why 0.101100111100 and so on is irrational? I always like to throw in a bit of history of maths when I can. It helps students see where things come from, that maths was discovered, is being discovered still. So having looked at the subset structure, let's look at what happened historically. First, of course, we have the natural numbers, starting at 1. Mathematically, 0 was quite a late arrival on the scene. You could ask students to find out about it. Then came fractions, the rational numbers, and then the irrational numbers, well known to the Pythagorean school around 500 BC, although they didn't like them. At this point, we've then got all the real numbers, but not the negative ones. It's interesting to note how late negative numbers come into the picture, accepted by mathematicians around the 17th century, about the same time as they realised that they needed complex numbers. I also find that in the end it's quicker to introduce the notation early. Students can get used to it, and it saves so much time. On the whole, I find they like being able to use the shorthand. It feels as though they're doing grown-up maths, and of course it saves writing so much. So, N for natural numbers, Z for integers, Q for rationals, that's Q for quotient, in case you were wondering, R for real numbers, and C for complex numbers. Students will ask why Z for integers, so it's useful to have an answer ready. Or again, you could send them off to do some research. They'll find out all about Nikolai Bourbaki, a fake mathematician with lots of publications to his name. So, it's about time we defined imaginary numbers properly. This is the definition. Why isn't it the same as defining I to be the square root of -1? Well, of course, the square root isn't well defined. It has 2 values. However, you will often see this definition in print, so it's about being aware of a higher level of precision. Some old A-level texts use J in line with the usage in physics and engineering, but there is universal use of I in the 2017 specifications. So, now we can square root any negative number. What's the square root of -144? Did you remember -12i as well as 12i? It's worth being fussy with your further maths students. It instills good habits in them. Now we get to our first wow moment for the students. All that time you've been telling them that they can't solve quadratic equations like this one. You've been lying to them. Pause the video for a moment while you have a go at using the quadratic formula to solve this equation. What happens? How are you now able to deal with it? OK, so using the quadratic formula, you get z equals minus 6 plus or minus the square root of 36 minus 4 times 25, which is 100, all over 2. And that simplifies to minus 6 plus or minus the square root of minus 64, all over 2. And of course we can now square root minus 64, we get 8i. So minus 6 plus or minus 8i, all over 2, which is minus 3 plus or minus 4i. So we get two solutions as usual. The really great thing about this is that it's barely beyond GCSE. Certainly there is nothing of A-level maths in it, just this one new idea that you can square root negative numbers after all. So now we found that we need to combine real and imaginary numbers like minus 3 and 4i into a single number, we get what we call complex numbers. Note that x and y in this definition are both real numbers. We can formally define the real and imaginary parts of our complex number z. Students struggle with this. They will try and say that yi is the imaginary part rather than just y, which does cause problems later on. So there is a need to be clear and precise. Here's another small wow moment. Pause the video while you work these out. Don't forget that I squared is equal to minus 1. OK, so I squared is minus 1. Multiply that by I to get I cubed, and that's minus I. Multiply it again by I to get I to the 4, and that's minus I squared, which is 1. Multiply by I again. Multiply by I again, multiply by I again, multiply by I again. So what about I to the 2003? Did you spot the pattern? Every fourth one we get back to 1. So I to any multiple of 4 equals 1. Which means that I to the 2003 is the same as I cubed, which is equal to minus I. The closure of a set under an operation is an important concept. Students don't need to know it explicitly, but it is useful to observe that, having introduced I, you don't need any powers of I ever in manipulation of complex numbers. That's the end of this first video. In the next section, we'll look at manipulating complex numbers.